Hello, this is Dr. David Kreller of the Chemistry Department of Chulalongkorn University in Bangkok, Thailand. In this chemistry video, I'm going to talk about the use of fractional composition diagrams to describe the equilibrium distribution of a weak acid between its deprotonated and protonated forms. So as we know by looking at the chemical equation, a weak acid has the ability to exist in the protonated form, of course, but if it reacts as an acid, it converts into its conjugate base. So there's these two forms present in solution simultaneously. If this is a weak acid, the deprotonated and protonated forms will both be present, and there will be concentrations of both of those forms. Now, of course, that's unlike a strong acid, which will ionize completely, but the weak acid will have, in principle, non-zero concentrations for each of these forms. It's convenient to use fractions to discuss how much of the acid is in deprotonated and protonated forms. Why fractions? Because once we get used to using fractions to talk about those concentrations, we can discuss the speciation in a concentration independent manner. In some cases, the behavior of an acid in terms of how much of it is distributed between protonated and deprotonated forms, say for example in a 0.01 molar concentration solution, it is the same fraction wise as the distribution in a solution that has twice the concentration. So it's efficient to talk about it in a concentration independent way. And we'll also see that we can use those fractions to construct what are called pH distribution diagrams. We have these two concentrations, the concentration of the protonated and deprotonated forms. And of course, if we add those two up, they will be equal to what's called the formal concentration of that acid, or the total concentration that exists there. So how are these two fractions calculated? The fraction that's in the deprotonated form is equal to that concentration of the deprotonated form divided by the total concentration. And similarly, the fraction that's in the protonated form is just equal to the concentration of the protonated form divided by the total. So the fractions, of course, will just be values without units from 0 to 1. And of course, like other good fractions, they will have to add up to 1. Okay, now let's look at the so-called pH distribution diagram. A pH distribution diagram, or can be called a fractional composition diagram, will have this sort of appearance. Now this is the appearance for just a monoprotic acid, which can exist in two forms. You see on this graph there's two curves. There will be one curve for each form. Here the curves are in blue and red, and they're labeled by this legend. Alpha is another word for fraction. So blue curve is for the fraction that's in the protonated form. Red is for the fraction that's in deprotonated form. And on the vertical axis, fraction just runs between 0 and 1. The fraction in the form, i.e. those curves, is plotted as a function of pH. So we can see how this diagram allows us to see how the fraction that's in the protonated and deprotonated form, how those fractions depend upon pH. So let's break this down a little bit. Think about the chemistry that's described by this diagram. Let's look at low pH. Well, low pH means high concentration of hydroniums. So let's look at this equation written this way. And high concentration of hydroniums will, in Le Chatelier's principal sense, push the equilibrium towards the left. And if the concentration of hydronium is high enough, it will push all the molecules into their protonated form. So that's why the fraction that's protonated always goes to 1 at very low pH. Every pH distribution diagram will look like this, unless it's a profoundly strong acid. But for most acids we talk about, we'll see the fraction of the protonated form go to approximately 1 at very low pH. Okay, at high pH, we'll rewrite the equation this way. We show the protonated version of the acid reacting with a hydroxide. Now, at very high pH, we have very high concentration of hydroxide in relative terms, which pushes the equilibrium to the right. And so if we go to high enough pH, high enough concentration of hydroxide, we can essentially push all of the acid into its deprotonated form. So that's why this red curve goes all the way up to about 1 at high pH. And simultaneously, of course, the amount that's in the protonated form drops down to 0. This is the type of question that I like to use in class when I'm using clickers and I've just freshly introduced this type of information. A question like this tests students for their qualitative understanding. I'll let you read that and answer it. Okay, low pH values favor the protonated. High pH values favor the deprotonated. So I guess that's D. Let's go back to this concept of the pH distribution diagram. So we've figured out why it's essentially got all the acid in its protonated form at low pH and all the acid in its deprotonated form at high pH. But let's look at this crossover point. They must cross over at some point because one curve is going from high to low. I guess that's the protonated form. It's going from high to low as you go to increasing pH. This other curve for the deprotonated form is going from low to high. So somewhere as you sweep through pH, those two curves must cross. And let's ask ourselves, what pH does that happen at? Okay, so we'll start with the acid equilibrium constant expression, and to answer this question, we'll take the negative log of each side of this equation, which is actually kind of partway towards converting that equation, I guess, which is sometimes called the Henderson equation. We're moving towards converting it into the Henderson-Hasselbalch form. But, okay, we've taken the negative log of each side of the equation. We've converted into this. So we can explicitly see, actually in this form, that the log term on the right here has the concentration of deprotonated over the concentration of protonated, as a ratio. So at that crossover point, those concentrations must be equal. That ratio is equal to 1. The log of 1 is equal to 0. So at that crossover point, that log term disappears. Now this is not just in general. We're talking specifically at one point. And at that point, the crossover point, the pH must be equal to the pKa of the acid. Here's another question I'd like to use in class. Which of the following conditions is not true for that crossover point? pH is equal to pKa. Well, that's true. This implies, since pH is equal to pKa, this implies that the hydrogen or hydronium ion concentration is equal to Ka. Okay? If those fractions are equal, they both have to be equal to 0.5. That's true. Let's skip down here. Hydronium ion concentration is 10 to the negative, raised to the power negative pKa. That's also true. It's D that's not true. A lot of people tend to, without really thinking about this, tend to say, oh, acid and base concentrations are equal when pH is equal to 7. But that's not true. Think about this carefully. We're not talking about concentrations of hydronium and hydroxide ions being equal. We're talking about the distribution of a weak acid between its protonated and deprotonated forms. And so this crossover point, we're saying the concentrations of protonated acid and deprotonated or conjugate base forms are equal, which is a different thing than talking about the point at which hydronium and hydroxide concentrations are equal. They're two separate things. So pH is not equal to 7. pH is equal to pKa. So the location along the pH scale of that crossover point depends upon pKa. So it depends upon the acid itself. And so along that line, furthermore, I like to ask this kind of question. Which Ka value in this list? So I guess there's 1, 2, 3, 4, 5 potential weak acids, and here are their Ka values. So this is the pH distribution diagram for which one of these acids. Well, I guess we can take that pH and turn it into hydronium ion concentration, which is 10 raised to the power negative 4.8, which I read from here as the approximate position of that crossover point. And that gives 1.6 times 10 to the negative 5 approximately, which is close to value D, which, by the way, is for the specific weak acid, acetic acid, which is the acid in vinegar. That brings us to the end of this video, so thank you very much for watching. Let you know that coming up very soon, we'll apply these concepts of the distribution of a weak acid between its protonated and deprotonated forms when we talk about buffers. Specifically, we're going to talk about what buffers do. So we'll talk about buffers in terms of their chemical composition. What chemical species are inside buffers that permit them to stabilize the pH of the solutions? And then finally, we'll talk about the chemical reactions that occur within solutions that contain buffers, or equivalently, you could say, are buffered. But that's what we will talk about next. So thank you very much for watching. We'll talk to you soon.